Hello and welcome. Welcome to the Nerissa webinar, Prepare Yourself for the Coming New Datums. I'm your host, Patrick Cunningham, GISP and Nerissa Director at Large Board Member. We're very excited to be presenting today with Dan Martin from NOAA and Blue Marble's own Sam Knight. So we hope to provide you a informational and educational webinar today. As you'll see that we have our agenda up already. I'm going to speak for a few moments and then I'm going to hand the reins over to Sam, who is our Director of Product Management. Sam's going to provide a Geodesy primer on datums and projections, and he'll be followed by Dan from NOAA, who will be presenting on the new datums that are coming in 2022 from NGS. Obviously, Geodesy is a very complex piece of subject matter. We won't be able to cover everything today, but our goal is to provide you with some of the nuts and bolts that are necessary to understand Geodesy, and then to follow that up with the news on the new datums, and to do our best to at least provide you with some helpful information in conjunction with our mission, Nerissa's mission, that is to provide education on GIS. Sam has been with Blue Marble now for over 12 years. He has led the development of our Geodesy training program, and he has trained hundreds of GIS professionals and surveyors on Geodesy and GIS software. So he's got a lot of background, and I think you'll find his talk to be very helpful. And Dan, of course, is from NOAA, and he's the Northeast Regional Geodetic Advisor. He's been with NGS since May of 2015. I'm sorry, he's been in that role since May of 2015. He's actually been with NGS since 2003, and he started his career as the Vermont State Geodetic Advisor. He was a past president and fellow member of the American Association of Geodetic Surveying. He's also a member of the Vermont Society of Land Surveyors and the New Hampshire Land Surveyors Association. As you can see, we have our Nerissa mission statement up here, just to give you a little insight about Nerissa as an organization. This is the New England chapter of Nerissa, and we're a professional association of GIS practitioners, and we're always promoting and talking about and trying to help promote GIS and information and education and technologies to solve geographic challenges throughout the New England region. And to do that, as part of our mission, we want to educate, we want to advocate, collaborate, and cultivate GIS and Nerissa and our community of GIS professionals and surveyors. So that's what's so great about this webinar today. It really ties into our mission, and the entire Nerissa board is very excited to be able to provide this for you all. If you want to learn more about Nerissa, please visit our website, nerissa.org. And as a side note, I wanted to point out that there will be CEU credits available for attending this webinar, and we will have more information available after the webinar is completed. And the webinar will also be hosted and will be available online for future viewing. And I'm not sure if we'll be able to make it available for download, but it will certainly be there, available at least through Blue Marble's YouTube channel, and I believe Nerissa will also host a copy on our website. And just briefly, I wanted to share with you the current board members of Nerissa. So if you have more questions about Nerissa or want to become involved with anything that we're doing, you can see that we have representatives all across New England. Please feel free to reach out to them. We're very happy to answer any questions and to provide more information on Nerissa activities. For the webinar today, if you want to ask any questions, your lines are all muted right now. You can just use the chat panel and in your GoToWebinar software, and And we'll answer some questions as we go, probably more towards the middle of the webinar. Sam will be able to start to answer some questions as Dan is speaking. And then we'll try to field some of the more appropriate questions at the end of the webinar live. We'll do our best to follow up on all questions if we can. We do have quite an audience today. Over 300 people are online right now with us, so we may not be able to get to every question, but we'll do our best. So with that, thank you. I'm going to hand things over to Sam now to start his portion of the webinar.
Okay, thank you, Patrick. So I am going to be talking about a quick primer for some basic geodetic concepts on datums and projections. Before we jump into that, we've actually had some of you asking questions already. We will be dedicating time at the end to field some of those questions, so feel free to use that questions tool to send them in. I think given the numbers that we have, there's always one or two folks who are having trouble working out the audio. I'd just like to take a real quick informal poll here. If you could use the raise your hand tool to let me know that you can all hear me okay. If you could just click that tool, looks like a little hand over on the right. All right, looks like we've got, most folks can hear us all right. So we're going to keep on trucking. This is being recorded, and Patrick mentioned we will be hosting it on the Blue Marble YouTube channel as well as the Nerissa page. We should be able to actually host it for download as well for offline use. And that's going to take us, usually it takes us just a little bit to clean up the video and get that posted and put up on the website. So we should be able to get that up there probably by midday tomorrow. So keep your eye out for that. So back to geodesy. So I'm going to be talking about datums and projections sort of on the academic level, sort of the user academic level. And Dan's going to get into the real practical stuff of what we're doing here in North America. So geodesy itself, what is geodesy? Really, it's a fairly simple definition of any typical academic subject. It is a science. It's considered its own science. Specifically, it's the science of measuring the size and shape of the Earth. The first half is figuring out the size and shape, and the second half is determining positions. That's where, you know, if you think of most of us who are GIS practitioners, we're charged with properly placing stuff on a map somehow. That is, most of us live in that second half of geodesy. Dan and a lot of the folks at the NGS spend a lot of their time in that first half, modeling the size and shape of the Earth and giving us all the ground rules we need to do that second half. Now, the stuff that I'm going to be talking about, the basics of the size and shape, the how we measure, the different types of measurements and stuff like that, this is an enormous topic. So we have about a half an hour here for my segment, and keep in mind we're going to be taking a very high-level look at this, and there's a lot more research, reading, learning that you can do outside of this setting. I'm going to point you at the very end. I'm going to point you at just a couple of resources that you can go to dig in a little bit deeper. And also, please do feel free to use the questions tool to put in stuff as we're going. The second piece that is, or actually the third piece of geodesy, is not just how big the Earth is and what shape it is, but how that is changing and evolving over time. So Dan is very specifically going to be talking about new models for how we deal with the size and shape and how we make those measurements. So that's really one of the newest cutting-edge pieces of the science of geodesy. So let's start talking about the size and the shape. The Earth can be described a number of different ways. It's had many different descriptions through history, one of which is calling it a pseudospheroid. And what that really means is something that is almost perfectly spherical, just not quite. So the size and shape we're talking about here, in radius around the equator, it's roughly 6,300 kilometers in radius. So an almost perfect sphere, roughly 6,300 kilometers in radius. Now, the variance in that is that it's wider across the equator than it is from pole to pole, and the surface undulates. And now the surface we're really talking about here, this image that we have of the surface of the Earth, this is a global model of a global sea level model. So if we're able to flatten out all of the terrain, ignoring all of the terrain, if we had a nice imaginary ocean that had settled out and covered the entire planet, what that would look like. And of course we are also looking at a highly exaggerated model here. If we back away from this thing far enough, it is going to look like a perfect sphere. We're talking about some fairly tight variants that we're doing all of this effort to establish these different geodetic models. Now that pseudo-spheroid itself, in modern times, we call this typically an ellipsoid, or if you're a land surveyor, you're probably a little more comfortable with the word spheroid. In modern work, in the GIS space, those are really the same thing. They're essentially synonyms in geodesy. Now the trick is there are differences depending on if you're talking about other mathematical fields. So in geometry, an ellipsoid is a different thing than a spheroid. In the geodetics world, they are one and the same. And we're talking about a simple diagram here. I have an ellipse, 2D ellipse. I have a major axis called A. That's the large one. That's why we call it major. The little one is called the minor axis. We call that B. We rotate the whole thing around B, and we assume that A is the same all the way around. Now, in geometry, that's not always true. A geometric ellipsoid could have a third axis coming right out of the page at us that we would call C. But in geodesy, we keep that nice and simple, and we assume that that major axis is the same, and that one is also aligning with the equator. So the wide part down at the equator. This was not entirely Newton's idea. Newton sort of did a pretty good job proving it. Basically, because the Earth was rotating, he said it's going to bulge out at the middle a little bit. And his term was an oblate ellipsoid of revolution. So basically, this 2D shape spinning around that minor axis and the three-dimensional shape that would occupy. So we're talking about a pretty subtle difference here. We have a diameter across the equator of a little over 7,927 miles. From pole to pole, it's right almost exactly 7,900 miles. So this 27-mile difference between, these two axes that are almost 8,000 miles across, we're talking about a difference of just 0.34%, and that is just enough to take sphere-based math out of the equation. So we have this term called flattening, and if it wasn't for flattening, we'd be able to use pi-based sphere math, and everything would be much, much simpler in terms of all these equations. So flattening itself, this is where we take something that seems nice and simple and we start introducing some complication back in. Flattening is this ratio that we have over here. So flattening, we describe that as a term called F, and we've set up a little formula here based on A and B, the major and the minor axis. So we subtract B from A, so we get the difference of those two, and then we divide by A. So this whole thing is called the ratio of the difference. And it's just a way of writing down those two dimensions, essentially. We could just write down A and B, but a long time ago somebody thought it was a better idea to write down the inverse of this, and that leaves us with this number that's right around 300 in most cases. So to describe some various ellipsoids that I've selected semi at random over here, we have the smallest ellipsoid that was used anywhere historically, and also the largest ellipsoid that was used anywhere historically. You'll see they have flattening ratios that are all pretty much similar values, just under 300, and in the case of this old French one, a little over 300. Take a look at these various radii that we have. This Plessis 1817, it's a very old one used in France. This is 6,376,000 meters. Take a look at the largest one we have, 6,378,000 meters. So of all these different ellipsoids, and there are about 90 ellipsoids that are used anywhere around the world still in modern historic mapping, they only vary by about 2,000 meters. So we're talking about something that's over 6 million meters in radius, and all of these various mapping systems we have only describe the size and shape by a 2-kilometer difference. Really, in modern times, most of those differences are down less than 1,000. So very, very similar models that we talk about anywhere on the planet. So we're really splitting hairs when it comes down to the different descriptions that we use to describe that ellipsoid shape. Now the ellipsoid is just an imaginary shape by itself. It doesn't have any place to start measuring from. It's not actually oriented to the dirt of the Earth itself. So when we take that ellipsoid and we tie it down to one particular spot on the Earth, we choose a place to center that ellipsoid around, and we give it an origin. That's how we turn it into a horizontal datum. And a horizontal datum is the first thing we can actually create a map out of. So it has a 0, 0 that we can start drawing our map out on the surface of our globe. This is a one-way relationship. An ellipsoid is not necessarily a datum. Ellipsoids can be shared amongst different datums. All we're talking about is various sizes and shapes that are used to model certain parts of the Earth. But if you have a datum, that means that you're using one and only one specific ellipsoid. So here in the States, we have some common ellipsoids that we use. In modern times, in the GPS era, we're using GRS-80 and WGS-84. Those are two ellipsoids that are almost perfectly identical. We have our older ellipsoid, Clark 1866, that was used in the horizontal datum, the thing we actually make our maps on, of NAD 27, the North American datum of 1927. When I say NAD 27, the horizontal datum, that very specifically means Clark 1866 and no other ellipsoid. It gives me an origin and a tie-down point for that one ellipsoid. If I were simply to say Clark 1866, that might be NAD 27. It might be the Jamaican datum called Kingston. Could be some of the Central American datums as well. So ellipsoids are used in multiple datums, but a singular datum definition has one and only ever one ellipsoid associated with it. Now, all those different origins that we could place down, all the different areas of the Earth we can scoot that ellipsoid over to, if we do that, if we give it different origins, if we orient the ellipsoid to different parts of the Earth, one position might have any number of different coordinates that could describe it. And so for that reason, latitude and longitude is not a unique identification of a position. It also has to be qualified with the datum that those latitude and longitude coordinates are relative to. Now the coordinate system is the thing that we actually build on top of the datum, and this is where our actual mapping takes place. So a geodetic coordinate system takes a datum and gives it the rules to measure out coordinates anywhere on the surface of the planet. So the rules are essentially what types of units we're going to be measuring in. And so if you think of latitudes and longitudes, most of us are probably thinking, well, it's just going to be degrees all the time. For us, here in North America, specifically in the States, down at the state level, we are using degrees. That is our convention. Throughout history, there actually have been a number of other angular units. Some parts of the world do mapping in grads, radians, microradians. There's any of these other ways that we've learned about in school. Other parts of the world have standardized on those. Most of us are talking about degrees. In the GIS space, most of our standards are based around degrees. So a geodetic coordinate system essentially is latitude-longitude measurements based on a horizontal datum. Now the key in a geodetic coordinate system are what kind of units are we using and where are we starting to measure from on the surface of this datum. So the equator and the prime meridian, very basic concepts, but they become very important for the context of our coordinate systems. So I'm not going to spend too much time on this one. These are pretty fundamental concepts that I hope everybody's already got. The equator, this nice imaginary line that bisects the Earth into northern and southern hemispheres, runs right around the middle at the widest spot. That's going to give us the basis for our lines of latitude. We take angular offsets measuring from the center of the globe out, angular offsets from that plane defined by the equator. Those are going to give us the basis of our lines of latitude. Because we're measuring our angle from the geocenter along the equatorial plane, those are going to go positive 90 degrees up to the pole, negative 90 degrees to the south pole. It is an imaginary line. It's not entirely arbitrary because it is a nice even widest spot of the planet. It makes a good bit of sense to start measuring from there. But the positive 90, negative 90 range, that's going to differentiate those from our east-west measurements, which are based on the prime meridian. Now the prime meridian itself, this is one of those really fundamental concepts in positioning. There's a lot of history around prime meridians. This is going to be something I'm going to point you at some extra reading towards the end. But the prime meridian is the one that most of us around the world use, is also known as the Greenwich meridian. So it was standardized back in the 1800s by a royal astronomer named Airy for the Royal Observatory at Greenwich, England. The short version is that the prime meridian is centered on the telescope that he made his astronomical observations from. For that reason, the prime meridian, the ultimate basis for how we measure east and west, is a completely arbitrary position. The reason it is where it is because it was a nice place to build an observatory. There's a good hill there. It's outside the city lights of London. It was a good place to build a building foundation to construct an observatory and then locate his telescope in that observatory. It is mostly imaginary. You can go stand on it. There's a brass bar in the ground that runs for a little good bit right through the middle of the observatory that very firmly marks it in the ground, but it is completely arbitrary. It is one of those things that we just all have to agree that we're going to start measuring from a particular spot on the planet. There are alternate prime meridians around the world, but in modern time we've essentially weeded most of those out, and most GIS software and most tools uses the Greenwich meridian as its starting place. If you ever get into international realms, you might run into a French meridian, you might run into a Spanish meridian. There are about a dozen others that are still used in various parts of the world, but mainly in historical mapping. Now, vertical datums, we've largely been talking about what we call a horizontal datum at this point. A vertical datum is how we measure our up and down. We don't often like to measure from the surface of that nice smooth ellipsoid because it's a little bit oversimplified. Ellipsoids don't give us a good measurement of up and down, specifically because of this concept of a line normal to the surface. So that would be a perpendicular line to the surface of the ellipsoid. Doesn't actually point to the middle. It doesn't model gravity very well for us. So a geoid model, and this is another one of those topics Dan's going to be speaking on specifically. A geoid model is how we measure our ups and downs. It gives us an irregular zero surface that's based on a whole lot of things, but gravity is one of the major factors. Sea level is another one of those factors, this idea that we have of a nice smooth ocean level. But the geoids are simply defined as offsets from an ellipsoid in most cases. So we have a nice smooth ellipsoid, we have our terrain surface that is this completely irregular shape, and then we have our geoid that does its best to model the gravity of the entire Earth or regional portions of the Earth. And because we're humans and the ocean is a nice practical thing for us, we pin that along the coastlines, and most of these we refer to this nice idea of sea level. Now the trick with geoid models and sea level is that geoid models are not the same exact thing as sea level. They just try to approximate it. There are also vertical models that are not sea level at all. We've had some questions get sent in ahead of the session about other tide references. So mean sea level, it moves around, goes up and down. The mean part of that is the average. So it's where the tides would settle out in the middle if they stopped moving. It is constantly a moving target. There is measured sea level rise in certain parts of the world, so those geoid models need to change over time as the oceans go up and down in some parts of the world. There is a lot of local variance that needs to be modeled. This graphic that we have on the right of the screen here, this is a map of the southeast coast of the U.S. here. This is actually right off of one of the NGS subsites. And the numbers that we have here, these are measurements in meters of the offset from the measured mean sea level at some coastal monitoring station and where the model of sea level, our North American vertical datum of 1988, where that model says sea level should be. So gravity, the oceans, trade winds, all of these things vary around the entire planet, and so it gives us what we call an undulating model. So there are these local variances that can't quite work into the model. So we're doing our best to approximate sea level or a tidal offset. There are low water marks, high water marks, the various cyclical marks that come in there. There's all these different places that we start measuring up and down. There are also vertical references that have nothing to do with the oceans at all. Some of them are based on inland bodies of water. Some of them are completely arbitrary, just leveling marks. Depending on where we are in the world, these have all different sorts of flavors. So Cartesian and projected systems, these allow us to do a lot of the stuff we actually do day in, day out in mapping. Projected systems, what we typically think of as our normal state plane systems, UTM type systems, any of our normal mapping systems, those are all projected systems. We're going to start off with a geodetic system, and we're going to wrap a Cartesian system around it. We're going to project the image of our globe onto a Cartesian plane, and that's going to do some interesting stuff that we're going to be taking a look at in just a minute. But this very simple idea of a Cartesian coordinate system comes at us in a couple of different ways. We think of a surface coordinate system typically as a 2D Cartesian system. This is where our origin might be somewhere on the surface of the planet. We have x going off in the west direction, x going off in the east direction, y going up in the north direction, and if we had a z-axis, it might be coming right out of the page at us, and we might be considering that elevation. Just very quickly, there is another way that we handle Cartesian coordinate systems, and that is in the pure Cartesian coordinate system sense. In this sense, our 3D diagram that we have over here on the right, these directions, what we think of as the cardinal directions, north, south, east, west, they go right out the window. The origin of our three-dimensional Cartesian system is the geocenter of the planet. X and Y are both on the equatorial plane. X protrudes out through the equatorial plane at the surface where we locate the prime meridian. Y is simply going to be 90 degrees offset from that. And then Z is our theoretical polar axis. So that's the axis that we theoretically rotate around. None of these axes really have anything to do with the surface other than X. It pokes out through wherever we locate that arbitrary prime meridian. Cartesian coordinate systems are endemic to how we use GPS. They're underneath the hood anytime we do a coordinate transformation in software. And they really are very active inside all of the things we do in GIS. We just don't often see them exposed at the very top level. Linear units at use in both Cartesian systems and projected systems. These are very, very subtle and very important to keep track of. For us here in the States, a lot of folks are very comfortable that the United States has our own linear units of U.S. survey feet. Some folks will call those statute feet, depending on where you are in the country. But a lot of folks are not aware that we actually do have two types of feet that are used here in the U.S. We have our U.S. survey feet, and we also have international feet used in the state plane zones for a number of states around the Union. Those diverge here out at the 5th decimal place. Where that gets to be a problem is not when we're just measuring 1 foot or 2 feet, but when we're using coordinate systems where our numbers fall into the ranges of millions and hundreds of thousands even in some cases. So what coordinate systems those are? Just about all of them. If you think about working in a UTM type system, our northings just about anywhere in the continental U.S., our northings in a UTM zone are typically going to be over 1 million. As we get up into the northern reaches, we get folks up into Canada or we get folks up into Alaska, they're going to be over the range of about 10 million. And so those small conversion factors become an issue in here. So just an important little side note to keep track of. Now, coordinate transformations. These come in when we have two differing geodetic models that we need to be working with. There are different methods of these. I don't have time to spend a whole lot on these, but there are differing methods, and the differing methods provide us different levels of accuracy. We're probably going to hear from Dan a little bit later on specifically about the transformations available for the North American systems. And you'll see I have those grouped down here at the very bottom under high accuracy transformations. The national standards that we have from the NGS, NADCON, HARN, and the horizontal time-dependent positioning system, those are all, each one of those is more advanced than any of the 3-parameter or 7-parameter, very basic types of shifts. The nuts and bolts of these are we're essentially trying to line up these different sized ellipsoids that are spaced in different places around the Earth. We're trying to line those up so that we can move between one or the other. Functionally, what's going on is these ellipsoids don't occupy different space, or they don't occupy the same space, excuse me. We're trying to describe the location of a point, and the point itself does not move. It's the description of that point through the center of the geodetic model, so the center of where those ellipsoids are located from their datums and how those are pinned down to the surface. The simplest version of that is a 3-parameter shift where we're working in that Cartesian space and we're trying to identify how far away the geocenter of one ellipsoid is from the other ellipsoid. The point doesn't move, it's just our description of the point that moves in a coordinate transformation. Now the practical end of a coordinate transformation is where our stuff goes at the surface. Now the ideal is that our point doesn't move, but because it's a transformation, our point is sometimes going to move. If we do it wrong, if we pick a poor transformation, or any number of other reasons that we've made not an ideal transformation on a piece of data. All of the points we have here on screen, this is basically your typical high school quarter-mile track. This infield here is the javelin field. You'll see the stripes they've put on there are 5-yard stripes. So from our green point, that's our starting point, coming outward here, all of these red dots represent starting from the same position and applying different transformations to that input data to get it from, in this case, I used NAD27 transforming to WGS84. You'll see the green dot at the very top. That's what happens when I use our correct national standard of NADCON. When I use any of these other ways to get from NAD27 to WGS84, there is an accuracy loss. Some of these transformations exist for various reasons. They all have different accuracies. Therefore, keeping track of which transformation you're doing is absolutely critical when transforming any data. And that's going to come up big time with these new systems that Dan's going to be talking about. Now, map projections. Map projections come after the geodetic system is established. So we model the Earth, establish its datum, come up with a coordinate system to describe it, and then we flatten that out. So it is completely dependent upon the geodetic model itself. When we have a new datum, or if we're changing datums at any time, that is going to affect the projection that we come up with. So all those things that we model in a projection, things like area, distance, direction, conformality of angles, all of these things are dependent upon that base geodetic model. So when we change the model, all of those measurements around it are also going to change. So there's going to be some pretty significant work coming along in the future for new coordinate systems from these. Terms around projections, just really quick. Convergence, measuring our angles on the surface, how we measure from grid north to true north. These depend on where our projection is centered, what type of projection we're dealing with. Multiple versions of north. North is not always where we think it is on the map. Having those two different types of grids, the projection grid versus our geodetic grid. Scale factor, as we're making measurements of areas, distances, things like that. One shape modeled on the surface of a globe is going to project out in a distorted sense onto our final projected map. Again, all of this goes back down, starting with the size and shape of that base ellipsoid model that we're rolling into this. Some projections that we commonly use around here in the States. Transverse Mercator, Lambert conformal conic, stereographic. There's one other little zone up in Alaska. I know we have some folks from Alaska. That's an oblique Mercator zone that is used up in those areas. All of these are used to model different properties, whether it's distance, area, angles, any of those 4 properties that we can maintain from grid to globe. Different purposes for these, and they're all dependent upon that geodetic base. We cannot escape needing to have that common starting point from all of our coordinate systems at the geodetic level coming out into our projections, where we actually do most of our work. Now, I'm sorry we had to speed through some of this. Half an hour is just enough time to really wet your tongue. For further reading on this, Dan's going to have some additional links coming up in his section. There's some really good, very easy to follow videos up on the NGS video library. In particular, there's a deeper dive on geodetic datums that really breaks down a geodetic datum, makes it very easy to understand, even for a layman. I mentioned a book about locating the prime meridian, setting up the basis of really all of our modern mapping. This book is called Longitude, The True Story of a Lone Genius Who Solved the Greatest Scientific Problem of His Time. It's a quick little read. You can probably knock it out in a good afternoon, I think. Patrick and I have both read it. He's nodding here. I think I actually borrowed it from Patrick. Yeah, it's great. Very interesting book. And then for those of you who really want to take a deep dive, there are two references at the bottom, Datums and Projections by Roger Lott and Jonathan Iliff. That is a very advanced, I will say it's an advanced but approachable book on geodetics, and as well a slightly older reference that's very common around the States here called Flattening the Earth by John Snyder. All of those men are very, very well-respected authorities in the field of geodetics. Really very good reference, and hope you enjoy encountering any of them.
I would just add to that. I believe it's Penn State's online GIS program. They have their first course in that series. The books are all online, open and free, and there's a good couple of chapters on coordinate reference systems as well. It's easy to find. So real quickly, before you hand things over to Dan, Sam, I just was thinking, what are, in support, we get a lot of support requests around coordinate transformation, and my data won't line up. When you hear that question, my data won't line up, what's going wrong? Are there a couple of things that you think of right off the top, that we're looking at? Is it?
Yeah, so, well, here in the States, we've, basically every country in the world has the same problems in that place. So there are definitely sort of hot buttons that take place. Here in the States, if stuff isn't lining up, first you need to sort of classify where exactly it's not lining up by how far is the first question. Typically in the States here, if you're within a couple hundred meters and you've just got a little bit of wiggle in your map, we start looking at datum issues. So NAD 27 versus NAD 83 or WGS 84, any of those common references. If we're really tight, if you're down, say, within about 50 feet, we start looking at units conversion issues, U.S. feet versus international feet, those sorts of things. A little bit farther away, sort of beyond that couple hundred meters scale, meters and feet start coming into play. If you're not even anywhere close, then we start looking at major projection issues, things like that.
So datum shifts, units.
Datum shifts, linear units. What projection zone are you in? Are you in UTM zone 19 and you should be in 18? Factors like that. There are a lot of places where it can go wrong. In all of the metadata for a single coordinate system, there's about 80 different pieces of information that build up a complete geodetic reference. Yeah. And we have to start with the easy things to screw up and start looking for the harder things to screw up. Okay,
well, we want to hand things over to Dan. There have been a couple of good geodesy questions, and we'll get to those at the end. But just in the interest of time, we should probably hand them over, right?
Yep.
Let Dan take over. And while you're doing that, one question was about the online course information I was talking about. It's from Penn State, the Penn State online course. For their GIS certificate, they have a couple of chapters on coordinate systems in their books.
All right, so Dan, I'm handing control over to you, sending you presenter control.
Yep, got it, Pat. There we go. All right, thanks Sam. Yeah, so Sam's Sam's presentation was a really good primer for what we're going to talk about here. It gives a good background on some of the systems that we're talking about, and it gives hopefully a refresher and a little bit of an understanding of sort of how these systems are developed to begin with. And what we're going to be talking about for the second half of this is some of it's in the development stage of these systems, but the other part of it is really sort of going towards the maintenance aspect of these systems. And we'll talk about that a little bit to see what that means. And that's, my agency, National Geodetic Survey, our mission is to define and maintain and provide access to the National Spatial Reference System. Okay, so the National Spatial Reference System, as we define it, deals with the items that you're probably most familiar with: latitude, longitude, and height. And there's a number of other quantities which Patrick, I keep saying Patrick, which Sam mentioned. Also, gravity being one, for instance, orientation and scale. For those who work along the coastline, you're familiar with something probably that's deemed the national shoreline. So that's like the official shoreline. It's a I say a physical location, but it is a measured location that has statutory type information about it. Okay, if you're talking about owning to a particular place on a shoreline. But as Sam started to allude to also, the other part of that is how these quantities vary in time. We certainly can create this datum, and it in itself is a static thing. However, the Earth is not static. The Earth is very dynamic, and as things move and change, we need to be able to incorporate that into our systems. So, by definition, these are sort of the groups that we are directly responsible to, as consider them customers, if you will. But our job to create the systems is for other people to do mapping. NGS themselves really don't. We don't do really anything having to do with mapping. We define the systems that everyone else uses, hopefully, so that we can all play on the same sheet of music. So Sam started and talked about these, what datums were, and we can think of a couple of things like NED 27 and NAD, the original NAD 83, going back to its origin of 1986. We really considered those to be horizontal datums. They were two-dimensional, right? We had a northing and an easting, or a latitude and a longitude. And then we had a vertical datum, NGV 29 and eventually NAVD 88, or local title datums that we use to describe our vertical. But what we really work in today, as surveyors do, most certainly, but our datums themselves are really three-dimensional, or in some cases four-dimensional if we talk about transitions through time. So we look at a latitude, longitude, and an ellipsoid height. I think we're all familiar with the fact that the North American datum 1983, or some of the international frames, ITRF or WGS 84, are a three-dimensional Cartesian coordinate system based at the Earth's geocenter, or at the center of gravity for the Earth, and it's a three-dimensional value. So that's really describing now what we refer to as a geometric datum, or a geometric frame. And like I said, where we really are today is being able to describe this fourth dimension, which would be to monitor and to model how those quantities change through time due to various things, either slow episodic type changes, continental drift, continental rotation, or something much more dramatic like an earthquake that displaces land quantities. So I'm not going to get into the weeds on this, but what is a datum? So there's really sort of two ways that you could describe a datum. One being the math and the constants that Sam talked about, and the second being the math and the constants and the coordinate system, the coordinates of the points themselves. The NGS has used the first definition for NAD83. You can see that it'd be very confusing if every time that we decided to do a readjustment, and we'll talk about some of those here in a moment, but every time we readjusted the coordinates for a point or points, we would have to create a new datum. Okay, so terminology-wise, I think a lot of folks are aware that we've gone through a number of different, we call them realizations, but think of them as a version of NAD83. And when we've released these new realizations, the general consensus, the general point of view of the public was that we were putting out a new datum, and that's not the case at all. It's the same datum, exact same mathematics, everything. The only thing that's changed is that we've readjusted the data that is tied to that datum. Okay, so just a little bit of a clarification on that. So if we look really briefly at the history of NAD83, originally completed in 1986, pretty much all consisting of classical observations, line of sight type observations, meaning from here in the east, from mountaintop to mountaintop. You know, long lines of triangulation, maybe a little bit of baseline measurement. And then in the 90s, we introduced the ability to use space-based technology, most notably GPS, and that's where we created really the first versions of what we call here in the east the high accuracy reference networks. Out west, there's a couple that are called the high precision geodetic network. But essentially they're the same thing. They're those highly precise points that were established in the 90s as sort of the backbone of our coordinate system here in the U.S. And then over time we've had different adjustments to these to what we define as the National Spatial Reference System. So we had the NAD83-86, we had NAD83 here in the east, we had NAD83-92, which was our first HARN. For most of the New England states and the Northeast states. Then we had, some of us had a readjustment done for that in 96. We had one then in a readjustment again in 2007, and in 2007 that included only the GPS observations. It didn't include the older terrestrial observations. And then most recently, not on this list, or actually I guess maybe it is, I'm sorry, it is our current epoch, which is the NAD83 2011 epoch 2010.0, and you'll notice that looks a little bit different. Although technically, if I were to go to the 2007 readjustment, that would have an epoch date of 2002.0, and essentially what that means is that data and those coordinates were computed to be good as of that date. So 2010.0 is midnight January 1st. Or December 31st, however you want to look at that, of 2010. So horizontal coordinates, you know, what do we use, right? Well, you might use latitude and longitude or state plane coordinates, and you say, well, I tie to NAD83, and that's good. Okay, that's what we want to do within the GIS environment. We need to define what it is that we're tying to. But the big question is which one? And Sam mentioned a few things here in follow-up to one of the questions, or to a question, about where do you start looking for problems if your data is not lining up. Well, what if it's not lining up at the meter level, or at the couple meter level, or at the decimeter level? Well, that's where these come into play, because we can see that as time has gone on, we've had all of these different adjustments of NAD83, or different realizations of NAD83. So the question becomes, what really is my data tied to? And maybe if your data is fairly, and I don't mean this in a bad way, but if your data is fairly coarse or low resolution, you're doing meter level or 10 meter level type mapping, sure, you could probably say my data is tied to NAD83 and no harm done. But it may not truly describe the accuracy of the data or what system your data is truly tied to. I think we're all aware today that we're using very high resolution spatial data within the GIS environment. The ability to do observations through real-time networks using RTK. We're now incorporating things like LiDAR, which has a decimeter type scale or even smaller horizontal type resolution as far as where we expect those points to be relative to each other. So when these products come in, I think it makes a real big difference as far as being able to document what these systems are or what your data is tied to. And I guess Sam said that there's like 80 different elements that properly describe things like datums and coordinate systems, and this is certainly one of the big ones. Some folks may still be working in NAD 27, and there may be a real need to do that. So that's there. Some folks might say that they're working in WGS 84, and that may or may not really be true. I think the only way to truly work in WGS 84, in my opinion anyway, would be if you're using autonomous GPS data with absolutely no correction, no post-processing, no real-time modifications to that data, or if you are working for the military and you're tying to a point that they've defined as a WGS 84 coordinate. And so if you are, excuse me, if you are and you're working in WGS 84, maybe you're doing work for the military and your mapping products are truly in WGS 84, that's okay. But you have to, again, go in and say, well, which one? Over the years, there have been significant changes to WGS 84, and these, by the way, are in fact, by definition, as Sam indicated, ellipsoids and datums. These are, in fact, different datums. It would have been nice, I think, if they had changed the name. That would really clue people in that it was truly a different datum. But it's not a readjustment. Each one of these represents a different geocenter. In 1987, the geocenter was exactly the same as the original NAD 83 of 1986. Or let's put it this way, NAD 83-86 was the same as WGS 84. Here, these are all just readjustments of data within the same datum. These are all datum changes because they relocated the geocenter. So the center of or the origin of, or where that ellipsoid, okay, where the ellipsoid is tied down to the center of the Earth has changed in each one of these iterations. So today, when we look at the geocenter here or here, which are exactly the same, okay, it has not changed. We have not changed our datum. If we change the location of the center, we'd have to change our datum. Okay, same ellipsoid, in this case, the same location. But this, but this and this WGS 84, G1674, or any of the international frames, these deviate by 2.2, 2.3 meters now. So if you're looking at a WGS 84 coordinate versus the NAD 83 coordinate, three-dimensionally there's a difference of approximately 2.2 meters. So along with these realization changes or datum change, when we're talking about 27 to 83, we're looking at a different accuracy, both from a nationwide network scale as well as a local scale, and the type of shift that we're seeing from system to system. So we can certainly see that as we've drilled down here over the years, this has become much more accurate, certainly on a network scale. From coast to coast, we had about a 10-meter resolution in 27. Just jumping to 83, even using the exact same data that was in the 27 frame, okay, all the old terrestrial observations, because we included a little bit of Doppler observations, so the first use really of space-based type measurements, that allowed us to get a scale resolution across the country of about 1 meter. So as we can see, we've gone, really, from 10 meters to 1 meter to 1/10 of a meter to the centimeter level on both a network and a local type accuracy. The other thing that's changed over time is how we've described the accuracy of these points. As surveyors, anyone who's a surveyor, you're very familiar with the one part in something, and that works very, very well for line of sight observations. If I'm measuring a line that's 10 miles long and I say it's 1 part in 100,000, that means something to me. Okay. If I measure a GPS point on the ground and I say it's 1 part in 100,000, okay, relative to what? Relative to a core station that's 50 kilometers away that I use to position this point, or relative to a point that's 5 feet away. So this this length relative accuracy concept really went away on our newer frames, where now we're looking at a 95% type confidence level for describing our accuracies, and both from just from a spatial standpoint and certainly within a GIS, these types of accuracy descriptions make a lot more sense.
Dan, could I jump in with a question?
Absolutely.
We had somebody asking if you could clarify specifically what that ratio of 1 to 100,000 means. What is that a ratio of?
So 1 to 100,000 would mean that if I had well, let's say 1 part in 1,000. Okay, so if I measured a line that was 1,000 meters long, and the accuracy that I'm stating for the coordinate or for that measurement is 1 part in 1,000, then that means I have 1 meter of error in that line. So 1 meter of error in a 1,000 meter line. Or if I say, quickly do the math, if I say 1 part in 100,000, that might mean that in a 1 kilometer long line, I have 1 centimeter of error. Is that correct? Did I take the right number of zeros off? But hopefully hopefully that describes what that means. And that's why I say it doesn't really work well for GPS data, where your observations are, if you want to think about it as an observation, is coming from 30, 50 kilometers away. That 1 part in, the reality is it's probably 1 part in 100 million or something. That doesn't mean anything to you looking at the data on your project and trying to figure out how well those points are going to match up compared to other points of either similar or dissimilar accuracies. So hopefully that explains that a little bit. If not, shoot the question back afterwards and we'll address it again. So that sort of takes care of the horizontal part, where we've come from. So what's a vertical datum? Okay, and I think Sam went into this, so we don't need to spend much time. But by definition, it's what we're defining as our zero surface. I could create an arbitrary vertical datum by driving a railroad spike into a telephone pole. Don't do that. They really don't like that. But you could drive a spike into a pole and call it 500 feet and use that, and that would be your datum. And that would put your zero surface at 500 feet below that arbitrary reference point that you put in. So essentially, it's just whatever. In this case, it's a surface, not a point, for the way when we're talking about our datums. So it's a full surface. The vertical datum, it's a system for determining the heights above that zero surface elevation. We use today is through certain things like what value of gravity are we assigning at a particular location, and the other physics that go along with gravity and gravity and the geoid, as Sam alluded to. And then the realization. Remember, we talked about with the horizontal or the geometric datums that we have these realizations. But the way that we realize the datum from a vertical sense is to physically access those points. So if you truly want to tie a project or make a measurement relative to NAVD 88, North American Vertical Datum of 1988, you means that you physically have to go out and touch a piece of brass or a benchmark, okay, that has been measured and has had a height established within the NAVD 88 system. Okay, so that's how we realize the vertical datum is by physical access. So with NAVD 88, the definition you can see is right here. This is how it's defined. Okay, and the 0 point or the origin is at a tide gauge, Point Rimouski in Quebec. And the realization of our vertical datum is over 500,000 geodetic marks with published NAVD 88 heights on them, all relative in connected measurements going all the way back to Father Point Rimouski, which was the one point that was held fixed. And I apologize a little bit, as Sam alluded to in his presentation, that there's a lot of information that goes along with this, and I've sort of skipped through some of the background on 29 and why we moved from 29 to 88 to begin with, and I'll point you at the end if there's some other information that's available that you could look at, but this is sort of a subset of a 4-hour presentation that I usually do, so I'm doing that in about a little bit less than a quarter of the time, so we had to get to the more meat things with the more meat on them. So we can use these systems, and we have used these systems, and for the most part, many people use these systems without any problems today. But there are problems both with NAD 83 and NAVD 88. We'll talk briefly about what some of these are. NAD 83, it's not as geocentric as it could be. Okay, we mentioned that it's about 2.2 meters away from where our understanding of the Earth's center of mass is today. Okay, so that's something that most of us don't see today. Okay, if we go out, if most people go out and they use a handheld GPS receiver, okay, or a recreational grade receiver, let's say, and you get an autonomous position from the satellites, it's good to, a number of meters. Okay, so this 2-meter difference doesn't really show up. Okay, so we don't see that. But the forecasts say that, in not too many years, I think most of us are aware that, we have GPS, we have the complementary system from Russia called Galileo, we've got the European Union putting up satellites called Galileo, GLONASS, I'm sorry, the Russian complement. Then we've got Galileo, we've got the Compass or Beidou from China, we've got systems going up from India. So in the not too distant future, there's the potential that there's going to be, 30, 40, 50 satellites available to us as positioning professionals, and the forecast is that it won't be unlikely that we can go out in the field with an inexpensive, go down to Walmart and buy your Ronco pocket GPS receiver / fishing pole, and go out and get a position on the ground good to a decimeter, maybe even better. Okay, when that happens, NAD 83 isn't going to cut it anymore. Okay, so we're trying to get, from a geometric standpoint, we're really trying to get ahead of the game here to make sure that we're ready to address this system, or these changes to the systems. NAD 83 is also not really well defined with positional velocities. We've got a little bit of an idea, especially in areas where we have large changes due to earthquakes, that type of thing. But from a quote-unquote static plate type thing, we call NAD 83 a static or a plate fixed system. But the reality is that there are movements going on within the plate, both horizontally and vertically, that are not these large events like an earthquake. We have these very small changes taking place here in the east. We have we have uplift, especially up in the Northeast. We have uplift due to the removal of ice after the last glaciation. You go down, you get up in the Great Lakes, and you've got subsidence. You get down into in the Gulf region, and you've got subsidence down there for two different reasons. Okay, so there are many things that are going on. We also have things like sea level rise. If we're talking about, a vertical datum that is supposed to essentially be our best idea of a global mean sea level, but yet we're aware that there are these changes, okay, to sea level, locally sea level rise, which is measured, it's documented, then do we continue to say that sea level is this, even though we know that the sea level is changing? So if we're tying our datum, our vertical datum, to some understanding of sea level, then we maybe need to have a better connection and the ability to make updates to this and to reflect these changes on as the changes take place along the coast. So, why isn't NAVD88 good enough? Well, a lot of it is because we use benchmarks. Okay, that's how we realize the datum. So, if you set a mark in the ground and you measure it and you walk away, you don't know that when you come back tomorrow it's in the same place. You don't know that it hasn't moved. A lot of these marks have never been, many of the marks here in the U.S. Or in the East for sure were put in, in the 20s, the 30s, the 40s, the 50s. Maybe, probably the last major leveling that took place was in the late 70s, early 80s. That's a long time. That's going on 40 years. A lot can happen to those marks over 40 years. A lot of them have moved. Okay, either maybe if it's not a really deep mark, maybe there's frost heaves or subsidence in the area. They get destroyed by the dozens due to we all love rail trails, but when you pull the rails out, all those benchmarks that were set along those rail lines, a lot of them get destroyed in the process. Highway construction, etc. So we lose a lot of these marks. They're not funded to be replaced by us. Extremely expensive to do geodetic leveling. They're not in convenient places. For anybody who has to use benchmarks on a regular basis is well aware that there's almost never one where you need it. It's always at least a mile away, probably many miles away. They don't exist really in Alaska. They weren't adopted in Canada. NAD83 was not adopted in Canada. They were determined by leveling from a single point, okay, from Point Rimouski, which allows errors to build up, uncontrolled errors to build up across the country. We did this for a very good reason. We don't have time to get into the reason that we did that versus the way that we had 29, but there were problems with the 29 datum, which caused us to make these changes. We know today that due to space-based gravity missions that can look at gravitational potential on a global scale, that what we selected as a zero surface for NAVD88 is biased by about half a meter. And we also know through that same technology that it's tilted, that our zero surface is actually tilted by about a meter across the country from, so let's say, from Florida to Washington. So these are some of the significant problems that we have with NAVD88 today. We could continue to use this system locally, and probably it would be okay, other than the fact that the benchmarks are being destroyed probably faster than they can be put back in. But on even a regional scale, we can see where these problems of this 50 centimeter bias and tilt in that surface on a large scale can cause some issues. So this is what NGS plans to do about it. We have our 10-year plan, which is last updated in 2013, and our target is to replace, this is redefined here, but to replace both NAD83 and NAVD88 with new systems. hopefully to achieve centimeter level accuracy to all coordinates, horizontally and vertically, customer-focused agency and global scientific leadership. So these are all things that are inside of our 10-year plan. So along with these changes, we no longer encourage the use of the term horizontal datum, but we want to call this a geometric reference frame, because this is truly what it is. It's a three-dimensional, four-dimensional frame. Geocentric, X, Y, Z, latitude, longitude, ellipsoid height, that's how we're going to be using it. Vertical datum, as reasonable as that sounds as a name, we're really encouraging, and what we're going to be using as a term is a geopotential reference frame. And I think if you've sort of followed along with the terminology both that Sam was using in his presentation and some of what I've talked about when we start talking about gravity, is the measurement of heights is exactly that. It's a measurement of geopotential, of gravitational geopotential. You know, the higher you are, the lower the gravity value. The closer you get to the center of the Earth, the higher the gravity value. So when we use gravity to define which way water flows, that's exactly what it's doing. It's flowing between these geopotential from geopotential, using the geopotential gradient in order to define which way that water is going to flow. The things we need to take into account is this undulation. As much as we think that sea level is a flat surface, right? I mean, if we go out into space, like Sam mentioned, and look, everything looks flat, everything looks round. And even when we're on a boat and we're looking across the horizon, you know, we see this curving surface. But the reality is that surface is actually undulating. It's lumpy and bumpy. And it's nothing that you can specifically say that it's not a flat surface, it's not a regular surface. It's very irregular, and it varies with the attraction of gravity. And then those will be reduced into orthometric heights, i.e. today NAVD88 or some other system, and gravity. These are the components that go into this new geometric frame. And deflection of the vertical, and I think I have a picture that sort of shows what that is. So the future of our geometric frame will be cores-based via GNSS or GPS, if you want to think about it that way. So you know what that's going to mean is that we're looking at using the NGS's continuously operating reference stations to establish all of our horizontal coordinates. Okay, coordinates and velocities will be in an international terrestrial reference frame, and some official U.S. datum, which will be directly linked back to the international frame. And again, we measure these velocities. We have transformation models that apply these velocities both from a plate tectonic rotational scale, and in many cases also from an event scale, i.e. earthquakes. Passive control will be tied to the new datum, not a component of the new datum. So today you can go out and tie to a Harn mark and say, I am tying to the datum. The only way to tie to the datum in the future will be to use GPS directly. Cores are computed, published daily, track changes, support development of real-time networks. So these are all sort of the components of the new geometric frame. The new geopotential frame, gravimetric and geoid-based. We don't have time to really go into geoid theory and how we do it today, but it'll be purely a gravimetric geoid, so it'll be just gravity. We'll be monitoring that and how it varies over time. We'll develop the transformation tools that are needed. So we all know today that we have this vertical transformation called VertCon to convert between NGVD29 and NAVD88. We'll be building other transformation tools that will help us go to this new vertical datum. We need to build a new gravimetric geoid model. This is our GravD program. Determine the gravity within, that doesn't really matter to us. And both orthometric heights and dynamic heights are supported. So for those folks who work along the Great Lakes, you're familiar with the international Great Lakes datum, which is a dynamic height system as opposed to an orthometric height system. So again, you know, we cannot go out and do this by leveling. It's too costly. Even if we did, the marks get ripped out. So the only way really to move forward both geometrically and geopotentially is through the use of GPS or GNSS. Okay, to do that, we need to have a very good understanding of our gravity field. Okay, so that's what we're searching for now is our best gravity field, our best geoid. And I'm just going to go quickly through this cartoon. Sam essentially showed the same thing. Okay, the relationships of our geoid height, our ellipsoid height, and the orthometric height. And this is that deflection of the vertical. So that describes the slope of the geoid at the location that the measurements are being taken. And the equation that we use for driving that quantity. Okay. So here's our GravD program. And again, it's very much like instead of making observations on the ground, it's much more like doing LiDAR or doing aerial photogrammetry. It's an airborne platform with a relative gravimeter on board that we can measure gravity while the flight's taking place. Some of the information we have, NGS 10-year plans available online, as well as the information for the GravD project, and some other support information, the socioeconomic benefits of CORS and GravD, which talk about the economic needs for that support the direction that we're going. We have a New Datums webpage on the NGS website, and as Sam mentioned, there are a number of videos and recorded webinars and that type of thing that have to do with the new datum, as well as datums and coordinate systems and geodesy in general. So I encourage you to look around. It's not always easy to find the information on our webpage, but there's a lot of stuff there if you're patient and you dig a little bit deeper. Let's see. So some of the predicted changes we're looking at. So this is just a little computation that I did for a point in Montpelier that looks like we would be changing by about 4 feet horizontally and about a little bit less than 3 feet negatively in our ellipsoid height. And then if we look at the ellipsoid height transformed to an orthometric height, we're looking at a little bit more than 1 foot change, and that's going to be different throughout the country. It'll go from essentially 0 to something over a meter, depending on where you are in the country, and maybe even more than that in Alaska. I'm not sure. I've never done the computations for Alaska to see what those differences might be. But this information is pretty easy to do. We've got some, I think we have some slides on this subject that show what those changes are, a shaded relief map essentially that shows what those changes are predicted to be across the country. So this is the argument that we have. I mean, we have marks that are in the ground, and we want them to be constant. We want to go back to that mark every day and say, I know the value on this mark is 1, 2, and 3. And the reality is, though, is over time, marks get destroyed. The values of those marks change through local motion in there, and you don't know that unless you survey beyond, or unless you measure beyond a local event. You may not even know that those events are taking place. So, when we can incorporate things like LiDAR, for instance, you can do change detection right through different LiDAR projects, or through aerial photogrammetry, or any of those type of measurement systems that take you off of the surface of the Earth. It's much easier to see that things are taking place that we may or may not be accounting for on a regular basis. Okay, so we really are moving away from the constancy and getting more towards retaining the accuracy, which means being able to make the changes when those changes are really need to take place. So again, just another cartoon that shows you the importance of that. So this is I think my last important slide here. Okay, it's really important today. Okay, if you want to use your data in 10 years or 5 years or 6 years, it's really important to document the heck out of it as far as your datum and the epoch of that datum, and even importantly how that data was secured. If you have a bunch of a bunch of information, let's say it's all heights, was that height determined by a surveyor through leveling or using a total station? Did it come out of a LiDAR project? Was it done with GPS using an ellipsoid height and a geoid model? The method of the way that data that those positions were determined is equally as important as the datum that they're tied to, because the methods themselves will yield different results. So what's next? Again, a lot of information on our web page, and that finishes it up. I think we still have some time for questions if either any came in or if folks are raising their hands. So I'll stay unmuted, Sam and Patrick, but I'll turn it back over to you.
Okay, great. Well, thanks, Dan. We've had a whole bunch of questions come in. I've been answering a few of them in the chat box as we've been going. Some of the ones that I can answer in 1 or 2 sentences. We've got a few basic pieces of commentary. A couple folks have mentioned from experience. Actually, something you mentioned just in one of your last slides there about the importance of metadata and recording epochs and the date of work being done, and all of that along with your data projects, how important that is. A few folks wanted to underscore that that significance. And let's see, so I'm going to back up a little bit. A couple of folks had some questions about specifically about transformations to NAD 83 2011. So let's see here. Neil and Ray were asking about transformations. One of them was having trouble doing some transformations in some software, and the other one is asking more in general. How is the best way to transform to the NAD 27 2011 current epoch? I'll jump in on a piece of this and then give it to Dan. So a lot of software right now hasn't quite yet caught up to the latest tools from the NGS. There is a toolbox from the NGS called HTDP. You saw Dan reference it a couple of times on his slides. That stands for Horizontal Time-Dependent Positioning. That actually is a conversion solution, transformation solution. It models all of the North American plate fixed frames against all of the ITRF and WGS84, all of the various iterations of each of those. There's about 20 different reference frames that HTDP allows you to move in between. NGS does have a portal where you can go to enter transformations in there, and those transformations are also available in some software packages. I don't mean to toot our own horn here, but at Blue Marble, in our transformation packages, we support that, and there are others out there that are starting to come online as well. So it is more comprehensive than what you think of as a typical datum shift. It is not quite so easy to do on the fly as some folks are familiar with talking about data reprojection on the fly, but there are tools out there for modeling that time-dependent shift. Dan, do you have anything else you'd like to toss in there about NAD 83?
Yeah, just a couple of things. As you mentioned, the HTDP, or Horizontal Time-Dependent Positioning, allows you to do frame transformations, but also takes in the temporal aspect. So you can give you can say even within the same frame, within NAD 83 or whatever frame, here's my coordinate today. What was it? Okay, based on plate motion, what was it? 342 days ago. Okay, so you can actually put in a date and transform coordinates through time in a dynamic frame. The other thing, when you talked about the on-the-fly part, and that's really where I think your metadata is is really, I think, critical. I think many of us have gotten into the habit of ingesting data, you know, by the terabyte, and our software is miraculously making these transformations. And we're making the assumption that we're feeding it the right information to begin with. The transformation models might be perfectly good in the software that you're using, but you're making the assumption that you're providing the right information, that you're providing the right coordinate system, the right foot unit, the right whatever it might be. So that's where really the more metadata that you can put with your data, the better it's going to be for everybody. And the last piece on this is NGS does officially have 2 products now that will allow you to transform from the last version, accepted version of your HARN, of your high accuracy reference network. So if you look at a lot of transformation tools out there, it might say, you know, NAD83 Vermont HARN, okay, or Indiana HARN or something. So what we've done is we've computed a transformation. I say we, Drew Smith at our agency has computed a transformation from the last realization of the HARN to the NAD83 NSRS 2007 realization, and that product is called GeoCon, okay, as in geodetic conversion, okay, GeoCon. And then we have a separate conversion or transformation that goes from NAD83 2007 to NAD83 2011, and that's called GeoCon 11. So these 2 products are out there. They're available. I think the newest version has the ability to upload a file of points in a freeform type format. And our intent is to start bundling these transformations so that you can just go in and say, here's my coordinate in NAD83 state plane east, or whatever the coordinate system might be. Give me my NAD83 coordinates in UTM in meters. Okay, and so we're working very hard to try to bundle some of these. But yeah, so if you look on our in our toolkit, look for GeoCon 11. That will help to get you to the most recent realization of NAD83.
Okay, great.
Yeah. So thanks, Dan. This is Patrick again. I just wanted to say that we're going to post a recording of the webinar, probably be on Blue Marble's YouTube channel and through Nerissa's website, and we will also post the presentations as well. But we do have a lot of questions, so we're going to actually keep going and answer a few more questions. I just wanted to let folks know that the information will be available afterwards. So I'll hand it back to you, Sam.
Yeah, the other thing.
Yeah, go ahead.
The other thing I'd mention. The other thing I mentioned too is that if there are any questions afterwards that don't get answered, and it's a question you think should be directed to me, please feel free to pop me an email, and we can handle these offline at a later date.
Great.
Yep.
So Sam, did you have some other questions?
Yeah, actually we have a follow-on to the HTTP. Is the HTTP system US-centric, or is it available in other countries to model plate tectonics? Now, to my understanding, Dan, we're able to do the time-dependent stuff here on the North American plates, and there is some function off of the North American plates, but it doesn't actually encompass the full time shift. Is that somewhere near correct?
I would have to go in and look at the parameters. I think that we do. Well, for instance, could you use HTTP in Austria? I don't know. I think the actual datum or frame transformation would probably be okay, as long as because even NAD83 is a worldwide frame. But you're right. The temporal aspect of it is geared specifically to the U.S. really.
Yeah, I think under the hood, HTTP essentially does 3 things, for those of you who are not familiar with it. 3 transformations, that is. It does 2 time shifts and then a frame shift. the frame shift is closest to what we think of as a normal datum shift. And I believe that portion works internationally, but just not the temporally related time shifts. So let's.
Yeah, I think that's essentially correct.
Yep. Let's see here. We had a comment actually from Dave Doyle, so we have a celebrity guest attendee here. Dave Doyle had a question, or not a question actually, he provided some extra information there for us on the use of international feet, so you can catch that down in the questions box. We had another question on, let's see here, really more of actually a sort of a comment / question from Joel. But to remove ourselves from constancy, we in GIS will have to be constantly shifting GPS projects to stay accurate. 2022 will be a very difficult time to mash up dependent surveys without holding NAD 83. And along with that, a few other folks have asked a similar question. So are we intended to move into this new sort of time-sensitive period with dynamic systems? Will the systems always be changing for practical mapping?
Well, I think there's going to be a couple, and I'm going to sort of speak off record here, but I think it reflects a lot of the conversation that I've heard within my agency. Is that I think from an agency standpoint, we're looking at being able to track these changes over time and make those changes within our frames when it truly makes sense. Okay, so that's one option. So, we could stay with whatever our new horizontal datum or geometric datum is going to be called. We can stay with an epoch of that until it becomes large, so large that we really have to account for it, right? I mean, so if enough change has taken place and people are starting to see those changes in the field when they're making measurements, then we obviously need to make a change so that doesn't happen. So that's one approach. The other approach is coordinates du jour, which we certainly could be in a complete dynamic frame if you wanted to. What I think what we're going to see is probably something leaning more towards the first option. But along with that is we're going to have, hopefully, a very good velocity model that will allow, should someone want to, say, yeah, I'm adopting this very first realization of the new reference frame. And as data comes into me, and I'm sure folks in California have to deal with this on a much more significant basis. But as data comes into me, tell me when the data was collected. I can take that, I can transform it in time to my quote-unquote stable frame if that's what I need to represent. So I think the capability will be there for us to handle, or for users to handle those situations and do what makes the most sense, I think, for them locally. But again, the important part of that is having that metadata and being able to manipulate that data sort of on the fly as it comes in.
Okay. We've got a few other different but all related questions. Some folks working with the IGLD datum, the International Great Lakes datum. How is this going to affect those folks? We've had some folks asking how this is going to affect working against USGS topo maps. Similar questions for what's this going to do to the specific transformations around Alaska, and also in general, what's this going to do to the state plane coordinate system? So a lot of endgame coordinate system questions. So what's happening?
Sure. Okay. Let's see. So the first one, I had the topo. What was the first one? I started writing it down. I lost the first question.
I think I was saying IGLD, the Great Lakes datum.
Gotcha. Yeah. Well, as was pointed out, I think in my presentation, whatever we are doing scientifically will incorporate and support dynamic height, so i.e. the system. I know, and I can't speak in great detail at this point because there's still unknowns, but I will say that IGLD is being supported, and it certainly is on our radar screen. There's an active project right now that is taking place that is on our project list, and when a lot of our projects are more exercises in mathematics, not necessarily field work. But there is an active mathematical project for determining how we are going to do and reflect dynamic heights using this new paradigm of GNSS observations in this gravity model. So I can't give you a full answer. All I can really say is that it's on our radar. It is being worked on, and it will be supported. That's we've agreed. I say agreed. We've are dedicated to doing that. The topo maps, to a great extent, I think what you're going to see is about what happened when we went from 29 to 88, except in the reverse. So historically, and this is part of my 4-hour workshop, but when we went from 29 to 88, one of the reasons that we picked the 0 height that we picked was to minimize the amount of changes that needed to take place to the USGS quad sheets. So essentially, when we picked our 0 and the location for our 0, i.e. in Quebec, that meant that most of the east had very small changes to the contours on the quad sheets, and most of the larger changes took place out in the Rocky Mountains, where it really wasn't seen. When you're looking at 20-foot contour intervals, you know, a meter and a half here or there didn't in the mountains didn't make didn't make significant changes. So I think that's probably what you would see again. I don't know exactly how USGS is handling that, although I know that we are working with them. They are part of the discussion that we're having at our every 2 years we have a gathering of all of the players involved on the federal level. The state plane coordinates, that is something that we are actively pursuing, and I believe we, if I recall, we actually have a document that has been released or will be released to the states, and this is something that was put together in partnership between NGS, the National Society of Professional Land Surveyors, and the American Association for Geodetic Surveying. What they've done is come up with model language that can be used in states' legislation for reflecting the changes, and hopefully putting it putting it in such a way that future changes to the language won't need to take place. So I haven't actually seen the final language, but you can anticipate something like using, instead of saying NAD 83, it might say something like the latest official realization of the U.S. reference frame, or however that wording might be. The other thing that when I go out and I talk to states and give workshops, I make sure that they're aware that this issue of state plane coordinates is something that the states themselves need to start to have these discussions. And I sort of kid, tongue-in-cheek, that NGS doesn't care about state plane coordinates. We don't use them. The users use them. So if Vermont or Maine or Massachusetts or Alaska want state plane coordinates, they will be supported by NGS, and we probably will take a lot of input on how you want those coordinate systems to be represented. Do you want it to be the same projection that are currently used, and you're going to change a false northing or a false easting for your in order to sort of shift it? We did that on the change from 27 to 83. We made a significant change to the false easting, for instance, so that when you were looking at a set of coordinates or you mapped 2 sets of coordinates, it was very obvious that you were either in 27 or in 83, or at least very likely that you were in one or the other. So these are some things that different state GIS groups and state government users, as well as the surveying societies, sort of need to get on the same page and sort of give NGS some input as to what you folks want to do with your individual state plane systems.
Okay, and I think we're going to wrap it up. I think we've got a couple of questions that I hope we can reduce down to just a couple of word answer, maybe a yes, no, or we hope so.
Okay.
What is going to happen between now and 2022? Will there continue to be modifications of new realizations of NAD 83 and the geoids?
Probably not, and I won't say that for sure. I think we're not looking to put out a new geoid model unless it's been deemed that there's a deficiency that we need to correct. So I think that's it. With that said, we're creating new experimental models all the time using the GravD data.
Certainly.
But as far as an official product goes, I don't believe we have any intention of doing that unless there's a real need or requirement. I also don't see a significant need at this point probably for releasing a new realization of NAD 83. I haven't heard any discussion about that. I'm not saying it wouldn't happen, but I'm not aware of anything.
All right, so we can we'll save all our coordinate transformation energy for a few years down the line. And the last one before we wrap up here that we're going to have time for. At 2022, with the release of the new models, are those going to be directly ITRF WGS84/GPS compatible when they hit?
Compatible, absolutely. Yeah, you won't have any issues there with. I mean, today NAD 83 is compatible with ITRF and WGS84. We have the transformations.
Yeah, I mean truly geocentric.
The new frame will truly be geocentric. Now, with that said, it may or may not exactly be the same as the current realization of ITRF. Again, these are some of the internal discussions we're having, but yes, it's the intent that the new frame will be. It will have the same geocentricity as some realization of ITRF.
Okay.
And probably the latest accepted realization at that time.
All right. I think that'll answer it. So again, apologies, folks. I know there are a lot of questions coming in all of a sudden. We do need to wrap it up and let everybody go. We do have all your questions saved. We'll do our best to follow up with those that we can. Again, we are recording this, so everything we've talked about so far will be hopefully posted on YouTube tomorrow and distributed out through the registration list that we had for today's session and also on the Nerissa website. We've had a couple of questions on the CEU credits. I believe that will be available on the Nerissa website as well. Is that right?
I think so. I think when we follow up with a follow-up email, watch for information on all of those points. And, you know, if you have other questions, you certainly can email us here at Blue Marble at info@bluemarblegeo.com. That's bluemarblegeo.com. And Dan, what's your email address?
It's dan.martin@noaa.gov.
And, you know, look for more of these kind of events, whether online or in our conferences. We have a Nerissa Day conference coming up in the fall, and I know Dan is speaking at events all the time around New England, and I'm sure other geodesists from NGS are doing the same about the upcoming datum change. And you know, as far as the software and data, we'll be able to support these transformations. Obviously, we want to be able to support them like any other system. So don't worry about that. That stuff will come down the road as we get closer. And so I just want to say a big thanks to Dan for helping us out here, and Sam as well, and everybody on the Nerissa board for helping us to put this together today. Thanks everybody, and thank you for attending.